Howdy! This is your friendly neighborhood physics teacher here, and I'm here to talk about your kinematics practice problems. Now, these are the practice problems for A Day. So if you're an 8A person, this is the video you need to be watching. I will do a practice problem for B Day. At the end of this video, I will be doing 16 and 17 of the mixed calculations, so you can see how those work. I'll be doing the A version of calculations on A Day, and I'll be doing the B version of the calculations on B Day. So I know it's possible, but if you're a B Day and you have the A version of calculations, this is the video for you. Just kind of skip through near the end. So we're going to do some practice problems, your homework practice problems, be specific. So the first practice problem I'm looking at is the race car one. So a race car is traveling in a straight line at 130 meters per second. So that meters per second tells you something. Hopefully you know meters per second is velocity. So this is one of your givens. So when you see meters per second, you need to think velocity. So your velocity, meters per second. Remember, we have two different types of velocity. So you have to think, will this be initial velocity or will this be final velocity? Since it's the first velocity it's mentioned, that's what it states the car is moving at, this will be our initial velocity. The problem continues to say, when the driver slams on the brake and decelerates, I hate that word. So decelerates just means accelerates in the negative fashion. And it is at a rate of negative 25 meters per second squared. So it flat out tells you that acceleration, deceleration, acceleration are the exact same thing. Deceleration and acceleration are the exact same thing. Just one is speeding up, acceleration. One is slowing down, deceleration. I still hate that word. Accelerates in the negative fashion. And so our A would be negative 25 meters per second squared. Meters per second squared. And just in case that some problems don't tell you, it's acceleration. Anytime you see meters per second squared, you should think acceleration. Meters per second squared goes with acceleration. Let's do part A. Part A says, how long will it take to stop the car? How long will it take to stop? Stop is another given. Stop is another given. So how fast are you moving when you're stopped? 0. Good job. Hopefully you answered. So it's telling you your final velocity. Your final velocity is 0 because it's stopping, which makes sense. The car is moving at 130 meters per second. It's slowing down at a rate of 25 meters per second squared, and eventually it comes to a stop. And our unknown is we want to know how long does it take to do all of this? We want to know how long it takes to do all of this. So now we need to figure out what equation we're going to use. What equation we're going to use. So I'm going to list our equation over here. So all the 4 equations that you could be using is delta x equals, skipping a part. Delta x equals vi times t plus 1/2 a t squared. Could use delta x equals 1/2 vf plus vi times time. You could use vf equals vi plus at, or you could use vf squared equals vi squared plus 2a delta x. So now we have to look at our equations. We need an equation. Okay, our equation has to have time. Our equation has to have time. That is a must. That is a must. So we could, that equation has time. That equation has time. That equation has time. Oh, this equation does not have time. So we cannot use that equation. Our equation needs to have initial, acceleration, and final. So what given are we missing? You do not see delta x in this mix. So we're not given delta x. So every equation that has delta x, we cannot use. So every equation that has delta x, we cannot use. So that has a delta x, so we can't use it. That has a delta x, so we can't use it. We've already marked this one out, but it has a delta x, so we can't use it. So the only equation that is left that we could use is the third equation. So let's go over here and use it. So VF equals VI plus AT. We have VF, it's 0. We have VI, it's 130. We have A, it's negative 25. And we're looking for T. So T just stays the same. At this point in time, we are done with physics. We are done with physics. It's officially now an algebra problem. It's officially now an algebra problem. So think algebra. Can we add or subtract these two numbers together? Hopefully you said no because of this t. T is being multiplied by 25. So we can't add or subtract because of that t. So we have to go ahead and subtract both sides by 130. So you get 130 equals negative 25t. Now we have to get 25 away from that t. So it's being multiplied. The opposite of multiply is divide. So you get t equals negative 130 divided by negative 25. The negatives cancel because you have a negative on top, negative bottom. Negatives cancel, and you're just left with 5.2 seconds. That is our answer. Now, to put that into scientific notation, we don't have to move the decimal at all. So it just becomes 5.20 times 10 to the 0 because we did not have to move the decimal. So there's our answer in standard form and in scientific form. So part B. Part B asks for how far will it travel in this time? So our givens stay the same. Our initial velocity is still 130 meters per second. Our acceleration is still negative 25 meters per second squared. And now we can add time to the mix because now we know time. Time is 5.2 seconds. And we know initial velocity, or final velocity, because of the word stop, is 0 meters per second. We know that because of the word stop. So we're pretty much trying to find how long it took the vehicle to stop. So we're looking for distance. So now let's go back to our equations. Let's go back to our equations. We're going to do a very similar thing, trying to figure out what we need. I have to rewrite some equations to get marked out. Wow. So that should be a t, that should be a t, that should be a t. So we're looking for delta x. So we have to have delta x with our equations. So we have to mark out any equation that doesn't have delta x in it. 1 has delta x. 2 has delta x. Oh, 3 does not, so we can't use the third equation. But then we need to look at all of our givens. We have initial velocity, we have final velocity, we have acceleration, and we have time. We have all other givens, so we can use either one of these. We can use this one, we could use that one, or we can use that one. Whichever one's easiest. Pick one. Now, the fourth one would be a little bit harder because delta x isn't solved for, but you could use any of them, whichever one you want. I'm going to pick the second one because guess what? It's the easiest mathematically. And why work harder when you could work smarter? So you're left with delta x equals 1/2 VF plus VI t. We're looking for delta x, so that stays. Our V final is just 0 plus 130 and our time is 5.2. So delta x, you're left with 1/2 times 130 times 5.2. You can just plug that into your handy-dandy calculator at this point in time, and you would be left with 338 meters. So that's our answer in standard form. To put into scientific notation, we have to move the decimal 2 times because we want there to be only one number in front of the decimal. So you have 3.38 times 10 to the 2 because we moved it 2 times meters. So there's our answer in standard and scientific form. Question 3. Question 3 is asking for the velocity of the car after 2 seconds. The velocity of the car after 2 seconds. So our initial velocity still stays the same, 130 meters per second. Our acceleration still stays the same, -25 meters per second squared. But in this case, our time is 2 seconds. We want to know how fast it's moving after 2 seconds. And so since it's when we want how fast, so that's velocity, so that'd be our final velocity. Again, let's look at our equations. So our equation has to have final velocity in it. Our equation has to have final velocity in it. So let's see if there's an equation that doesn't have final velocity in it. Well, the first one does not have final velocity in it, so we can't use that. The other 3 do. But if we look at our givens, we are missing delta x. Delta x is not in our givens at all. See? No delta x. No delta x. So we cannot use that one, and we cannot use that one because they have delta x in it. The only one we can use is the third equation. So we'd use v final equals v initial plus at. We substitute. You're looking for a v final. Your v initial is 130 plus your acceleration, which is -25, times your time, which is 2. Think about PEMDAS, because at this point in time, it's just an algebra problem. So PEMDAS, you do 25 times 2, which gives you 50. Can't forget about that negative. And then you have 130 minus 50, which you're just left with 80 meters per second. To put that into scientific notation, you have to move the decimal over 1 to get one number in front of the decimal. So you get an 8.00 times 10 to the 1, that's how many times you moved it, meters per second. And that is our standard and scientific form. That we're done with question 1. Question 2 states, what is the acceleration of a bicycle that changes its velocity from 12.1 meters per second to 23.5 meters per second in 7.81 seconds? So let's pull out our givens. So we were given initial velocity and final velocity. The initial velocity is the first one mentioned, 12.1. The final velocity is the second one mentioned, 23.5. It also mentioned time, which is 7.81 seconds. Our unknown is mentioned at the very beginning. It says, what is the acceleration? So we're looking for the acceleration. So again, you would look at your equations, and you would see that we need acceleration, so we can't. So if we go up here, we look at our equations, we need acceleration. So if you look, the second one does not have acceleration in it, so we cannot use the second one. Again, our givens, we are not given displacement, so we cannot use anything that has displacement in it. So we're left with the third equation again. So our equation is final velocity equals initial velocity plus at. This point in time, you just plug in. Final velocity is 23.5. initial velocity is 12.1, plus you're looking for your acceleration, your time is 7.81. Again, you cannot add these together because of the acceleration. So we have to get everything on the other side. So you subtract both sides by 12.1, and you're left with 11.4 equals your acceleration times 7.81. We want the acceleration by itself. They're being multiplied. The opposite of multiply is divide. What you do to one side, you got to do the other. So your acceleration will equal 11.4 divided by 7.81. And you plug that into your handy dandy calculator, and you get 1.459. That rounds up to 1.46. That is meters per second squared. That's in standard form. We do not have to move the decimal at all because there's already one number in front of the decimal, so we didn't have to move the exponent. Didn't have to move the decimal, so your exponent is 0 meters per second squared, and that is your standard and scientific notation of that. That's question number 2. Question number 3, you have a part A and a part B, and we're looking for what is the magnitude, so displacement, of the motorcycle, and it's given you a couple of givens. So A says determine at a rate of negative 4.35 meters per second squared. So it decelerates at a rate of negative 4.35 times 3. Can't read all of a sudden. Negative 4.35 meters per second squared. So that's your acceleration. Remember, deceleration, acceleration are the same thing. And also that meters per second squared tells you acceleration. That meters per second squared tells you its acceleration. And it says from a speed of 38.1 meters per second to a speed of 17.6 meters per second. So again, we have our initial velocity and our final velocity. Our initial velocity would just be the first number, which is 38.1 meters per second. Our final velocity would be the second number, which is 17.6 meters per second. Which makes sense because the initial is bigger than the final, and it says it's slowing down, so that makes sense. And we're looking, at the beginning it stated that we were looking for the displacement. So we need to look at our list of equations, and we need an equation that has, the equation has to have displacement in it. So that equation has it, so only the third one does not have displacement in it. We also are not given time. So since time is not a given, we cannot use the first or second one because they both have time. The only one we can use is the fourth one. So looking at our fourth equation, which is VF squared equals VI squared plus 2A delta X, we have your final velocity, which is 17.6 squared, equals your initial velocity, which is 38.1 squared, plus 2 times your acceleration, which is negative 4.35 times delta X. So now, again, it's purely an algebra problem at this point in time. So think about PEMDAS. So we have to do the squareds first. So 17.6 squared is 309.76. You do 38.1 squared, and you get 1,451.61. And then you could go ahead and multiply by 2 times your negative 4.35, and you get a negative 8.7, and that's multiplied by your delta X. Again, you cannot subtract those two numbers because of the delta X. So you have to bring your 1,451 over. What you do to one side, you got to do the other. And so you take your 309.76, subtract that by your 1,451.61, and you get a negative 1,141.85, and the other side is just negative 8.7 delta x. That's being multiplied. The opposite of multiply is divide. The negative's got to come with it. And then you just divide those two numbers, and you get a 131.25 meters. That's in standard form. Put in scientific notation, move it over 2 times. So you get a 1.31 times 10 to the 2 meters. And that is your standard and scientific notation form. B. So B, we're still looking for displacement. We just have different givens. It says it accelerates from rest at a rate of 3.67 meters per second squared for 12.1 seconds. So that from rest is a given. That from rest is a given. Rest, you're not moving when you're at rest. So that is telling you your initial velocity. Rest, so your initial velocity is 0 meters per second. It says you're accelerating at a rate of 3.67 meters per second squared. And it gives you time, which is 12.1 seconds. Your unknown, we're still looking for our delta x. So we need to go back up and see what equations we could use. We have to have delta x in the equation. So we have to have delta x. So we need all the equations that do not have delta x. Well, that's the third one. But we do not have final velocity. We do not know our final velocity. We have our initial velocity, and we have time and acceleration, but we do not have final velocity. So the equations that have final velocity, we have to x out. So the only one that we're left with is the first one. So our first equation is delta x equals vi times time plus 1/2 at squared. We substitute. We're looking for delta x. Our initial velocity is 0. Our time was 12.1 plus 1/2. Our acceleration was 3.67. Our time is 12.1 squared. Do not forget to square it. And again, at this point in time, it just becomes an algebra problem. So 0 times any number is 0. So that just goes to 0. And then you have to do the squared first. So 12.1 squared gives you 146.41. And now you can just multiply. So you take that times 3.67 times 1/2, which gives you 268.66 meters. Put that into standard form. You have to move the decimal over 2 times. And that gives you 2.69 times 10 to the 2 meters. If you notice on your key for the homework, the key is wrong. The key says like 22 point something, but this is the correct answer. And we did take that into consideration while grading, so it should be marked right if you had this, and even though the key might have said it was wrong. But that was an oopsie on our part. So that was question number 3. Last question, question number 4. So a spaceship is traveling above the Earth at 250 meters per second when it must decelerate to enter the Earth's atmosphere. If it accelerates in negative 35 meters per second, how long will it take to stop before hitting the Earth's atmosphere? So again, this is very, 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 very similar to number 1. Like, extremely similar to number 1. We have our initial velocity, which is 250. It's decelerating, so our acceleration is going to be negative, which it is, a negative 35 meters per second squared. It's stopping, so we know our final velocity is 0 because of the word stop. And it's asking for how long. So how long is time? Think about how long am I in this class for? So you're trying to figure out how long, much longer you are. So how long is time? Using our givens and unknowns, we can figure out what equation. So the equation we'll use is V final equals V initial plus AT. It's the only one that does not have displacement. So we don't have displacement, so we can't use it. Our V final is 0. Our V initial is 250. Our acceleration is negative 35. And we're looking for T. Again, we cannot add or subtract these two numbers because of the T. So we have to bring the 250 over. What we do to one side, we got to do the other. And we need the 35 on the other side. It's being multiplied, so the opposite of multiply is divide. So you just do negative 250 divided by negative 35. The negatives end up canceling, and you're left with 7.14 seconds. To put that into scientific notation, we do not have to move the decimal at all. So your exponent is just 0, and there's your standard and scientific notation form. Part B is asking for how far did it travel in this time. So our givens pretty much stay the same. Our initial velocity is 250 meters per second. Our final velocity is still 0 because it's still wanting to know how far it took to stop. Our acceleration is negative 35 meters per second squared. And now we know time because we just solved for it, 7.14 seconds. Our unknown we're looking for is delta x. At this point in time, we have everything, so we can use any equation that has delta x in it. The only one that doesn't is the third one. So you could use the first, the second, or the fourth one. Let's use the first one since we used the second one in the last one. So delta x equals VIT plus 1/2 AT squared. So your delta x, we're looking for your initial velocity is 250. Your time is 7.14. Your acceleration is negative 35. Your time is 7.14. Don't forget to square it. At this point in time, you have to do PEMDAS. So you can square the time, and you're left with 50.98. You can go ahead and simplify the 1/2 and 35, so you're left with 17.5. It's negative, and you can go ahead and multiply the 250 times the 7.14, and that gives you 1785. You need to simplify the 17.5 times 50.89. That gives you 892.15, and then you just subtract your 1785 minus 89 or 892.15, and you're left with 892.85 meters. To put that into scientific notation, we move it over twice. And we have delta x equals 8.93 times 10 to the 2 meters. And that is your standard and scientific notation form. One more. You're looking for the velocity of the spacecraft after 3 seconds. Again, a lot of our givens stay the same. Our initial velocity is still 250 meters per second. Our acceleration is still negative 35. But in this case, our time is 2 seconds, and we're looking for our final velocity because we're trying to figure out how fast it's moving after it moves for 2 seconds. So equation-wise, we have to use the equation that does not have displacement because we do not have it, which is the third equation. We're looking for our final velocity. Our initial velocity is 250. Our acceleration is negative 35, and our time is 2. We have to do PEMDAS, so you multiply first. So you do 35 times 2, which gives you 70. Don't forget it's negative. So then you subtract the 250 minus 70, and that'll end up with you with 180, except your... I wrote down a given wrong. This is what happens when you're looking at the wrong version. So your time should be 3. So let's do 35 times 3. Why didn't anyone say anything? No, I'm joking. Y'all can't say anything. It's a video. Haha. So 250 minus 105. Then you get 145. There we go. That's the right answer. That's why you should always double check your givens, which I did not on this case. To write down your scientific notation, you have to move the decimal over twice. So you're left with 1.45 times 10 to the 2 meters per second. Okie dokie. So now this is the point in time that I promised y'all I would look at 16 and 17 on these videos for you for mixed calculations. They're a little bit different, so I'm doing the version A of the mixed calculations. I'm doing version A. So on 16, says Sarah throws a ball straight up in the air with an initial velocity of 19.62. So our givens, it says right out the back, says initial velocity is 19.62 meters per second. And how long will the ball be in the air before Sarah catches the ball? So she throws the ball straight up, and then it comes straight back down, and she catches it at the exact same spot. So when it's at the very tippy top, its velocity is going to be 0. Its velocity is going to be 0. So let's figure out how long it takes it to go straight up. So we're going to say our final velocity is 0 meters per second. Our acceleration is negative 9.8 meters per second squared because that's the acceleration due to gravity. That's at the rate it's falling at on Earth. And we are looking for time. This looks a whole lot like almost every other problem on the work we've been doing. We're going to use the third equation. So our final velocity is 0. Our initial velocity is 9.62. And our acceleration is 9.8. We're looking for time. Again, we cannot add or subtract that because of the t. So we have to bring over the 19 over. And it becomes negative. And then we need to get the negative 9.8 over. It's being multiplied. The opposite of multiply is divide. So we're left with 19.62 divided by 9.8. And you're left with 2. But that is the time it travels only in the upwards direction. What does the ball have to do now so she can catch it? It has to come down. It's going to fall at the exact same rate as it goes up. So if it goes up at 2 and then it goes down at 2, we have to add those together. So this is basically that becomes time and a half. So your full total time that it's traveling will be for 4 seconds. The full total time it's traveling would be for 4 seconds. That's for 16. 17, 7 seconds. So on 17, Sarah throws the ball a second time straight up in the air with initial velocity of 19.62 meters per second. However, this time she lets the ball land on the floor 1 meter below where she threw the ball from. How long will the ball be in the air before it hits the ground? So now Sarah has missed the ball. So it goes an extra 1 meter. So what we need to figure this out is to know how far the whole entire distance, of the ball fell. That's what we need to find out. So ultimately, we need to find our whole entire displacement. But to do that, we have to find this part displacement first, this little tiny part of displacement. So let's figure out that little tiny part of displacement. So a given, in this case, our given is, our initial is going, our given are pretty much the same. Our initial velocity is 19.6. meters per second. We know time. Our time is in 2 seconds. So we're just trying to find that little tiny spot. Our acceleration is negative 9.8 meters per second squared. And we're looking for displacement. That becomes our unknown. So looking at our displacement, we need to know, we can use our second equation, because we have to use any equation that, we can actually use any equation. So we can use our second equation. So delta x equals 1/2 v final plus v initial t, no squared. That's from the first one. We're looking for our displacement. Our final velocity is 0. Our initial velocity is 19.61. And our time is 2. So at this point in time, we can just plug it into our handy-dandy calculator. And we're left with 19.61. Because guess what? The 2 and the 1/2 cancel. We're left with 19.61 meters. So this little tiny snippet up here is 19.61 meters. So the whole entire distance ends up being 20.6 meters. So now we have that whole entire distance there. Now we can find the time. So given, we're going to make our initial velocity 0. Now, the reason we're making our initial velocity 0 is because at the very top, it's 0, because the ball's not moving at the very top. We don't know final. We know acceleration is negative 9.8 meters per second squared. We know our displacement is 20.6 meters, and we're looking for time. That's our unknown. We are looking for time. So we do not have final velocity. The only one that does not use final velocity is our first equation. So our initial times time plus 1/2 at squared. So our distance is 20.6. Our initial is 0 times time plus 1/2 negative 9.8 t squared. So 0 times anything just equals 0. And you could go ahead and multiply 1/2 times 9.8. That gives you 4.9 t squared. And you just need to get the t by itself. So you divide negative 4.9, divide negative 4.9. Remember, the displacement is negative because it's moving in the negative direction. So that is a negative displacement. That cancels. You're left with t squared equals 20.6 divided by 4.9. And that gives you 4.2. You have to get rid of that squared. The opposite of squared is square root. So you square root your answer, which is 4.2, and you're left with 2.05. Now, this time is the only time it took it to fall down. We have to add the time it took it to go up, which is 2. So we take our 2.05 plus 2, so our answer becomes 4.05 seconds. Hopes that helps you out on your mixed calculations. Have a wonderful day. Bye.